Hello everyone. What we're going to do today is continue with some problems from chapter 4. Hopefully the concepts of the probability mass function, cumulative distribution function of a random variable, the expectation of a random variable, expectation of a function of random variable, variance, etc. are pretty clear to you. And upon doing more practice problems, those ideas would be pretty solid then. Okay, so what we're going to do is start with basic problem from chapter 4. We're going to do problem number 21. Okay, I'll read that out to you first. 4 buses carrying 148 students from the same school arrive at a football stadium. The buses carry, respectively, 40, 33, 25, and 50 students. One of the students is randomly selected. Let X denote the number of students who were on the bus carrying the randomly selected student. One of the 4 bus drivers is also randomly selected. Let Y denote the number of students on her bus. Compute expectation of X and expectation of Y. Okay? All right, so you might not have caught all those numbers if you're not following along in your book. So we have 4 buses. Okay, first bus has 40, next 33, 25, and 50 students. What you do is you look at this whole collection of 148 students and you pick a student at random and you ask that student, how many students were on the bus you were on? What's that student going to say? The student could say 40 or 33 or 25 or 50 depending on which bus he or she came from. Okay, so X is this random variable, which is the answer that student gives you of the number of students on his or her bus. So what's the range of the random variable X? The range of X will be 25, 33, 40, or 50, correct? Now, when you look at all these 148 students standing around, 50 of them are from this bus. So with what chance will you be picking a student from that bus? Since there's 50 from that bus, 148 in all, the probability of picking a student from bus 4 is 50 over 148, right? And similarly, the probability of picking a student from bus 3 is 25 over 148, bus 2, 33 over 148, bus 1, 40 over 148. Okay? So you can write down, what does this correspond to? Well, when you pick a student from bus 4, what's the X value going to be? The X value is going to be 50. So you can write these probabilities down. The probability that X is 25 will be the probability of picking a student from bus 3 so that will be 25 over 148. The probability X is 33 in the same way is 33 over 148. The probability X is 40 over 148. And the probability X is 50 over 148. Okay, does this make sense? So now what do you have? For the random variable X, you have all of the probabilities associated with every value in the range. So you can now calculate the expected value of X, which is the sum over all the numbers in the range of X, where you're looking at the sum of the product I times the probability X equals I, or the probability mass function of the random variable X evaluated at I. Okay, so what's this going to be? 25 times the probability X equals 25, which is 25 over 148, plus the next one in order. 33 times the probability x equals 33 is 33 over 148. Plus 40 times 40 over 148. Plus 50 times 50 over 148. Correct? So what are these values? Let's see. 625 plus 1089 plus 1600 plus 2500 over 148. So that is 5814 over 148, and that is approximately 39.28. Okay. All right. Now let's look at the other part. Okay. What's the other part? The other part is to do with the random variable y. What is a random variable y? Well, what you have is 4 bus drivers standing around. You randomly pick a bus driver and ask her, how many students were on your bus? The bus driver can answer 25 or 33 or 40 or 50. So, you know, and that's the random variable y. So what's the range of y? The range of y is going to be the same thing, 25, 33, 40, or 50. Now, what is the probability that y is any one of these numbers? Well, there's 4 bus drivers. You would pick any one of them just as likely as any others. So the probability that y is 25, or the probability that y is 33, or that it's 40, or that it's 50, they're all going to be a quarter. Okay? So now you have all the probabilities for all the values in the range of y, so you can also calculate the expected value of y. Well, before we calculate that, just let's stop for a second and think about this intuitively. What do you think is going to be bigger, the expectation of x or the expectation of y? So let's go back and look at the picture of the bus again, okay? So you have 148 students, and they are distributed in the buses like this. Let's just suppose they've gotten off the bus and are standing in a gathered circle over here. You randomly pick a student. Now, with what probability are you going to pick a student from this large volume bus? That's going to be with probability 50 over 148. So it's more likely that the student's going to answer x equals, or we'll give the value of x as 50 rather than give the value of x as 25. So since these larger numbers have more weight probabilistically and these smaller ones have less weight, the weight is just proportional to the value, it seems like intuitively it must be that the expected value of x should be higher, because with y, they all carry equal weight of a quarter. With x, this one carries weight 50 over 148, this one 25 over 148, and so on. Okay, so let's just quickly take a look at what y, expected value of y, turns out to be. So this will be a quarter times 25 plus a quarter times 33 plus a quarter times 40 plus a quarter times 50. You could just factor out a quarter and you have the sum of all the students on all the buses, and we know that's 148, and this divides nicely, and this is going to be 37. So that's the expected value of x, and this is approximately the expected value, this is the expected value of y, and this is approximately the expected value of x, and as you would have thought intuitively, this in fact indeed is bigger than the expected value of y. Okay? Well, I hope that problem made sense to you, and I want you to try and do problem number 23, which also uses this kind of basic calculation. So it's not the same kind of problem exactly, but it uses the same kind of basic calculations with the discrete random variable and the probabilities. Okay. So what we're going to do next is problem number 53 from chapter 4. I'll read that out first to you. Approximately 80,000 marriages took place in the state of New York last year. estimate the probability that for at least one of these couples, part A, both partners were born on April 30th. Part B, both partners celebrated their birthday on the same day of the year. State your assumptions. Okay, so what do we have? The scenario is 80,000 marriages took place. So you have 80,000 couples. And part A says, what's the probability that at least one couple has both husband and wife have their birthdays on April 30th. Okay, so how do we do that? First, let's figure out what's the probability that for one couple, what's the probability that both their birthdays are on April 30th. So what would that be? So what the probability that the man has his birthday on April 30th and his wife has her birthday on April 30th. We're just going to assume 365, and the probability that both husband and wife have their birthday on April 30th will be 1 over 365 for the husband and their independent birthdays. That's the assumption we're making, that people's birthdays are independent. And his wife's birthday's also 1 over 365. Independence, you want the probability of the intersection of the event that the husband has April 30th birthday and the wife has April 30th birthday, the intersection of that. So the probability is the product of the probabilities. So that's 1 over 365 squared. Okay, what we will do is we'll call this the probability P. This is the probability that any one couple has their birthdays, both the husband and wife have their birthdays on April 30th. Okay, so what's the deal now? We have 80,000 couples, and let's call that N. Probability that the couple both have their birthdays on April 30th is 1 over 365. We're interested in the number of couples where this occurs. So if X is the number of couples where this occurs, X will be binomial random variable with N equals 80,000 and P equals 1 over 365 squared, correct? Okay. So what do you see? We want the probability that there's at least one couple. So the probability X is bigger than or equal to 1. Now, obviously, we're not going to sum up from 1 to 80,000. This is a small enough number. So clearly what we need to do is 1 minus the probability that there are no couples where this happens. Okay, so what is this actual probability that there are no couples where this happens? It will be 80,000, choose 0, 1 over 365 squared raised to 0, 1 minus 1 over 365 squared raised to 80,000. Now, these two will just be 1. And this will be the answer to this part. So 1 minus that's the actual answer. These are not numbers that you want to deal with. It's a number raised to 80,000. That's not so easy to compute. And in situations like this, since you can see this P is very small, N is 80,000. What is N times P? That's 80,000. Times 1 over 365 squared. This I've calculated before already. This is approximately 0.6. Okay, so that's NP. That's a moderate number. So what we'll do is we're going to do Poisson approximation to this binomial. Okay, so probability X equals 0 is approximately the probability that a Poisson random variable with lambda equals 0.6 is equal to 0. Okay, so what is a Poisson random variable with lambda equals 0.6? What's the probability? That equals 0, e to the minus lambda, lambda to the k over k factorial. So that is this probability, okay, which is exactly just e to the minus 0.6. And we're interested in the probability x bigger than or equal to 1. So that is 1 minus the probability x equals 0. So that's approximately 1 minus e to the minus 0.6. So that's your answer for the probability x bigger than or equal to 1. Okay? Now, I want you to try and do part B yourself. What do you have in part B? Part B says that what's the probability that both partners celebrated the birthday on the same day of the year for at least one of the couples. Okay, so I'm just going to get you started. What's the difference in this situation? In this situation, all you're doing is here's 80,000 couples. What's the probability that for at least one of these 80,000, both of the partners have the exact same birthday? So both husband and wife have the same birthday. So now you're not going to have the restriction that you want the birthday on April 30th. It could be January 1st, January 2nd, September 29th, any of the 365 days. So whatever be the man's birthday, doesn't matter. The woman's birthday exactly has to be that. So what you have to do is adjust the probability P and try and find out what these calculations are. We can discuss this problem in class after you've given it a go. Okay? All right, so I'm going to stop this video for now. And if any of you have any questions, email me and I will try and send you a solution for that problem. Okay. All right. Bye.